So the support vector machine is a linear classifier, and what does that mean? So it's a linear classifier which means that given some input, some set of inputs x, such that xi's are in some d-dimensional space, and some corresponding labels y to yn, where y's are either -1 or 1, right? Then it'll be able to correctly separate the xi's according to the yi's, right? So visually, if we have some data, let's say that these are the negative examples and these are the positive examples, then the support vector machine will learn some kind of line like this, okay? All right, so this is in 2 dimensions. In multiple dimensions, this would be a hyperplane. So the equation for every hyperplane looks like this. So w, I'm going to put it z here. Z plus b is going to be equal to 0. So for any input z, right, that satisfies this equation, z will be in the hyperplane defined by this this equation, right? So w can be thought of as like a slope type of thing, and then b is like the separation from the origin. So in order to correctly separate our examples, given some input xi, what this means is that this should give us a value greater than 0 if the corresponding label is positive, and it should be less than 0 if the label is negative, right? So if it's less than 0, then the point lies somewhere below the hyperplane, and if the value is greater than 0, then the point lies somewhere above the hyperplane. Okay, so we can put this concisely as this, in this form. Wxi plus b is greater than 0, right? Okay, so that's the idea behind a linear classifier. Now, the thing that sets a support vector machine apart from a normal linear classifier is that instead of just having a normal line separating the negatives and the positives, we have what's called a margin, right? So this is kind of like a margin of safety. Instead of having this hard, like very thin line, which might not separate the classes very far from each other, this line, with this margin, we're able to have more optimal separation. So, so the only difference with the equations here is that instead of this equation having to be greater than 0, it has to be greater than 1 if the label for the sample is positive. And similarly, this equation will evaluate to be less than -1 if the label is negative. Okay. All right. So then we can put this into this form again to be more concise. Xi plus b is greater than 1, right? So this is what we want in that classifier. This is our constraint. Now, a support vector machine tries to maximize the distance from the hyperplane, the distance from the points of the hyperplane. So one way of describing this is we want to maximize this margin, right? So this is called the margin. Now, the margin is the distance between this plane and that plane. We can calculate the margin by taking some arbitrary point along one of these hyperplanes, adding some normal vector to it to bring us to the other hyperplane, and then just calculating the distance, the length of that vector, okay? So we can do it like this. Let's say we start at this plane right here. If we have a point on this plane, then that point will satisfy this equation. Plus b plus 1 is equal to 0. Here I'm just moving the plus 1 from over here to this side, all right? And then to bring us to the other hyperplane, we're just going to add some normal vector CW to the original point x. Okay. Now, why is there a CW here? The W is a vector which is normal to both of the hyperplanes, and then the C is the multiplier which just brings us from one hyperplane to the other. So really, we want to find the length of C. If C is longer, then the hyperplane is going to be larger. Okay, so we want to find out what C is with respect to W and B. Okay, so putting these two equations together, we'll get this. And I'm just going to distribute this here. Okay, we can get rid of the b's here. We can get rid of the wx, and that'll leave us with WCW is equal to 2. Okay, so solving for c, we get 2 over w times w. Okay, so that's what we end up with. This is the margin, and we're going to want to maximize this. So note that maximizing the margin, maximizing 2 over w times w is going to be equal to minimizing its reciprocal, right? So this is the same thing as minimizing this. So this is going to be our goal here, and this is going to be our constraint. So putting it all together, we get the primal form of the SVM, right? So the primal form is going to be minimize 1/2 w times w, right? And we want to find the w and the b, the kind of the coefficients and the bias, which minimize this equation, subject to the constraints that we want all our data to be correctly classified in this using this hyperplane. So remember, this is if all the data is correctly classified, then we should have this. Okay, so this is the primal form of the SVM.